5, 4, 3, 2, 1.
Hey everybody, welcome back to NASA in Silicon Valley Live. I'm your host, Abby Tabor. And if this is your first time joining us, NASA in Silicon Valley Live is a conversational show out of NASA's Ames Research Center. And this is where we talk about all the nerdy NASA news you need to know about. So today I have with me my lovely co-host, Allison.
Hi. Hi, everyone. I am your co-host, Allison. If you didn't know, we are simultaneously live on Twitch, YouTube, Facebook, and Periscope. But if you want to participate in the chat and ask our guests questions, there's only one place you can do that, and that's at www.twitch.tv/NASA.
Yes, and I'm sure you're going to want to ask questions because today we are dealing with one of life's biggest questions. Seriously, we're going to talk about, are we alone in the universe?
Yeah, this is such a great topic.
Yes.
I'm sure everyone will agree. And today we have some really amazing guests with us to talk about it.
Yeah, hi. Hi, everyone. I'm Alfonso Davila. I'm an astrobiologist here at NASA Ames, and I search for life on other planets.
Excellent.
And I'm Michael Furlong. I'm a roboticist here at Ames, and I build intelligent robots to explore other worlds.
How cool.
So, Abby, before we get into the show, how about we remind our audience about our cool clock right here?
Yes, exactly right. So this right here, this beautiful thing, is our moon countdown clock. That's because 5 years from now, in 2024, we are planning to send humans to the moon. That's part of our Artemis program. And this clock is counting down the days, hours, minutes, and seconds until we send the next man and the first woman to walk on the moon's south pole. So we will talk about that later in the show, but if you want to learn more, you can always go to www.nasa.gov/Artemis. All right, so let's get right to it. Is there life beyond Earth?
Well, short answer, we don't know. And that's the reason why we have to search.
All right.
But I will say this, the more we explore, the odds are looking better and better that we might find something out there.
They are. I'm glad to hear that.
Wow.
Yeah, well,
Exciting.
think about it. 30 years ago, what did we know about other planets and the possibility of life out there? We knew there was one planet that is inhabited, us, the Earth. Mm-hmm. There was another planet, Mars, that maybe yes, maybe no. We're not really sure. And that was the extent of it.
Okay.
Fast forward 30 years later, we know that there are moons out in the outer solar system around Jupiter and Saturn that have subsurface oceans of liquid water. Wow.
Yeah.
And we know that there are millions of planets around other stars, some of them the right distance from their sun, that liquid water could be stable on the surface.
Okay.
So these look like very promising places to look and to look and search for life.
So more and more opportunities, places we might find something.
The more we learn, the better it gets.
Outstanding.
Which brings the question, like, what is life? How do we even define it?
Well, that's a complicated one. Fundamentally, it's chemistry, right? We're made of chemistry, molecules interacting, reacting, doing things that allow those systems to survive. And so when we search for life, we're essentially looking for that type of chemistry. Ideally, because it's easier to find chemistry that is similar to us. But obviously, there's chances that whatever life chemistry is out there, it might be very different.
Oh, wow.
What's your perspective as a roboticist on this, Michael?
Well, I mean, it's a hard problem to begin with, but especially for sending robots out that are going to be doing exploration for us instead of having humans looking at all the data coming back. Actually, like, trying to quantify so a computer can say, yes, this is life, is a massive challenge in and of itself. And I think it's fair to say we don't really have a good way to do that just yet.
No, we know. And if the question is already difficult, imagine trying to answer the questions with robots, with surrogates, not with humans doing the actual experiments.
Yeah.
So that's the real challenge.
Like you say, you have to teach a machine to be able to do that.
You really do, to do these things that you can sort of instinctively do, but it's hard for you to write down, this is how I did that.
Yeah. Fascinating.
Well, where would you go to look for life? If you were going to go out there and really place your bets on the best place to look, where would you go?
If I have to pick one place, Mars is still top of my list.
Yeah?
Okay.
Yeah. And the reason is because Mars is close enough to the Earth that we can actually study it repeatedly. We've been sending probes to Mars almost continuously for the past 20 years. And that's given us a very good perspective and idea of how the planet is today and how it was in the past. Good enough that we know now that Mars, in many different aspects, is very similar to the Earth. It's a very familiar place. Mountains, volcanoes, meteorite impacts, sediments, rocks that are composed of the same types of minerals that rocks on Earth. And so it looks like at some point the conditions for life to exist on Mars might have existed. And if that was the case, those forms of life might have been similar to us. Similar enough that we might recognize.
Okay. Similar to some kind of Earth life.
Yes, not something completely alien that we wouldn't be able to recognize even if it was staring at us in the face.
Okay.
So Mars is a good candidate for those reasons.
Oh, wow.
There's some comments about that already.
Yeah.
Gibbs MT, take me to Mars, please. Hobbs 555, I hope there is human life on Mars in my lifetime. So first the robots are going to go.
Yeah.
And
Fun
then-
fact: there is life on Mars that we know of because obviously every mission that goes to Mars carries a tiny bit of bioburden in it. So
Okay, some Earth microorganisms or something.
Yeah. But,
Okay, so technically.
Technically.
Yeah, all right.
Well, Michael, what do you think the odds are of actually finding life on Mars? I mean,
Honestly, like we've taken samples now, and so far we haven't found definitive proof of life, and so the odds don't look great. But that's because it's a very big planet, and we're sort of sifting through it like grams at a time. So that's different though than asking what's the probability that there is or was life there to be found.
Yeah, that's a good point. And it's important to recognize that when you look at Mars and the history of Mars, it is really a tale of two different planets.
Really?
Mars today is a very extreme environment. A lot of people think that it cannot sustain life, at least not near the surface. But the more we learn about Mars, it tells us that way back in the past, it was a very different environment where water was flowing on the surface, where there were lakes, maybe seas, even maybe oceans, not too dissimilar to lakes and seas and rivers on Earth. And so conditions in the past might have been a lot better for life. And so it is this dual history of Mars, this dual perspective of Mars that we need to consider when we think about life on Mars. Early life in a friendly environment, or more recent life in a very unfriendly environment.
Yeah, I see. So yes, if it was friendlier in the past and life did emerge, maybe we would find fossil evidence
One
of that
possibility
somehow.
is that we find fossil evidence of it. Another possibility is that when conditions on the surface became extreme, that life retreated to other places, maybe deeper in the planet.
Underground.
And it's still trying to survive in those environments.
Ooh, yeah.
That's very exciting.
That is exciting.
Yeah.
Really Bad Teeth asks, is there enough sunlight reaching Mars in order for it to sustain healthy plant life? Or will we have to rely on artificial growing processes?
Well, when it comes to sunlight, that's not a problem. That's not a limiting factor. There are, in fact, microorganisms on Earth that can survive hundreds of meters deep in the ocean with very tiny amounts of light, a lot less light than what reaches Mars. So sunlight, not an issue. We would need to worry about things like temperature and radiation and other and toxic elements in the ground for those plants to grow. But sunlight,
So it's got enough sun.
yeah.
All right.
Can I ask one more question from the chat here? Twitcher asks, "What is life? Does it have to have a nervous system or brain or both?"
Well, I don't think so. Some of us don't have a brain, and we can be called alive. Most of the history of life on Earth, there were no brains and no nervous systems. It was microbial life, single-celled microorganisms. And in fact, if anything, the example of life on Earth is telling us is that being a single-cell organism without a brain and a nervous system might be a good thing because they've been around for billions of years.
Oh, yeah.
Brains and nervous systems have been around for a lot less time. And so, yeah, definitely not required.
Excellent. Good news. Because maybe
You
there's
gotta like
something
microbes, though, right?
Right. I know. Don't dismiss those microbes. They
Don't
might be
know.
the
They're-
ones
they're
able
important.
to survive out
They're
there.
important.
Right. All right. So should we talk about an early NASA experiment in life detection?
Sure.
You guys want to talk about Viking?
Yeah, I mean,
One of my favorite
Viking
ones.
was a really cool mission. So there
Yeah.
were two robots we sent to Mars. They were the first actually U.S. vehicles to land on the surface there, and it was about 40 odd years ago in the 1970s, and they were these largest structures that landed there, and they took pictures of the surface, and they tried to collect soil samples and did some really interesting biological experiments there.
And I think we have a photo of the Viking lander. Can
Yeah, we
see
do. Let's
that?
get a look at that. Viking lander. There it is.
Yeah, so you can see the lander, and there's a human in there to give you a sense of scale. And what he's holding up is the arm that extended out of the Viking lander and scooped up the soil that was then brought back into the vehicle to be experimented on.
Oh.
Yeah.
I think we have another photo too, maybe of it on Mars.
Yeah, because Viking took the first images on the surface of Mars, right?
Very exciting.
It's not this one, but things like this. And look how red it is.
Yeah, the
that
red
must have
planet.
been spectacular to see in the 1970s. So that's the arm that was collecting soil?
Yes, yeah, it's grabbing the soil out in the scene there.
Okay. And then what did it do with that? That was part of an experiment?
That was part of a very cool experiment. The first experiment to search for life on another planet. No
crazy.
more and no less. Viking did a lot of cool stuff. It took a lot of pictures. It showed us Mars up close for the first time. But the biological experiments is what really made the mission truly exciting. And there were 3 biological experiments. One of them is particularly interesting. It was called the labeled release experiment.
Labeled the release, all right.
Labeled release experiment. That was an experiment. That the idea for the experiment was that the arm with the scoop would scoop some dirt from the ground and put it in a container, and then add a solution, which was called a chicken soup.
A chicken soup.
Chicken soup
This
solution.
is chicken soup
And
that
this
you
is
brought.
chicken soup. And this is an example of one of the vials that was made in 1974.
It has a date on it.
has a
doesn't
date
it?
on it.
Yeah, what is
Yeah,
the date on that?
1974,
July
July
3rd.
1974.
Yeah, look at that.
And this is vintage chicken soup from 1974.
Why is that chicken soup? There's no rice, there are no
There's
carrots.
no rice, no carrots, no potatoes.
It's perfectly clear.
It's chicken soup for microbes.
for microbes, all right.
And so the idea is that think about it. If you are in a cold, if you have a cold or you're cold and you're starving and you're dehydrated and you're miserable at home,
Yeah.
what's the best thing you can have? A warm cup of chicken soup.
And
And so the thinking at the time was that microorganisms on Mars, if they were present in the soil, they would be dehydrated, no water, very cold, very low temperatures. And so to help them come back alive and actually be able to detect them, we would add this chicken soup so the microbes would have something to feed on,
Yeah.
grow, and then we would be able to measure the gases that are produced as they eat the chicken soup.
So that's what the experiment did.
That's what the experiment did. Add the chicken soup to the soil and then sniff the gases that would come out of the microbes chewing on the molecules like sugars and amino acids, all the yummy stuff that microbes like to eat, and was added with the chicken soup.
All right. So you're looking at traces of them digesting, if you will.
Yeah. So in our first evidence of life on another planet could have been microbial poop.
Microbial poop. Fantastic.
Why not?
Nice.
Something all life does.
Yeah.
Well, yes, I guess that's fair to say.
It is, yeah.
And so,
Well, yeah,
what happened?
Don't leave us hanging here.
Yeah, it was really interesting, and it was very inconclusive.
Oh.
So the observation, it was a very interesting observation. When the chicken soup was added to the soil, there was a chemical reaction almost immediately, and gases were released. And the same types of gases that you would expect microbes to produce if they were present. That was interesting and exciting.
Yeah.
The problem was that the rate at which those gases were released was odd. Was way too fast, almost instantaneous.
Oh,
If you
okay.
expected microbes to be present, they should take their time to come back up alive and eat their things, and then eventually release those gases. So that was odd. The other odd thing is that part of the experiment was to scoop out another sample of soil and heat it up to very high temperatures to kill everything that might have been living there, and then add the chicken soup. If the original reaction was due to biology, we shouldn't see a reaction in the second case.
Right, 'cause you would have
because
killed
everybody was dead.
Well,
And what happened was quite the opposite. They added the chicken soup to the dead sample, and there was a reaction similar to the first one, suggesting
Okay.
that whatever was causing the reaction was not a microbe.
shoot.
Yes.
That must have been crazy. You sent your experiment on a rover to Mars, and it gets there, and it does its thing, and you're not sure.
And you're not sure. I mean, you never know. Maybe they didn't like the soup.
Yeah, well, maybe
Who
that's it.
knows?
They
No,
like
but-
tomato soup, you know?
But definitely the experiment was very interesting, very inconclusive in that
Right,
sense.
right. So then what?
Well, it was clear from Viking that maybe our thinking about searching for life at that time was a bit naive, because we really didn't know much about Mars until Viking went to Mars.
I see.
Now, hindsight is always 20/20. So with what we know now, we might think it was naive. At the time, it was probably a very smart thing to do.
Yeah. Well, we hadn't been there yet.
We
so.
hadn't been there yet. So, but what followed up after Viking was a realization that when next time we search for life, we might want to know in advance a bit more about the planet, what conditions are there, and what the history of the planet was. And so a lot of the follow-up missions try to bridge that gap, that knowledge gap, understand what happened to Mars over the course of its history, how it became the extremely dry, extremely cold planet that it is today, and maybe try to understand if life was present at some point, whether it could still be there, maybe in other places, or maybe the chances of life surviving throughout Mars's history were pretty much zero.
Yeah. How'd you go from oceans to desert?
The deserts,
basically, right?
exactly, and how does life react to that?
Yeah. Fascinating.
So we've had a lot of robotic missions to Mars since then, right, Michael? What have we done over there?
Well, we've sent a lot of rovers to the surface now, and the latest one now is Curiosity. And that's going and actually collecting samples and driving around. It has a bunch of instruments. It has a drill on board for collecting samples. It has a laser for zapping rocks. So
I think we have a video of that, or an image, right?
Yeah.
There we go.
Here's
Oh,
Curiosity.
there it is.
Yeah.
Yeah. And the thing that personally excites me is that Curiosity has the ability to choose what it zaps with its laser, which is pretty neat.
It's exciting.
So
It's roving
robots-
around,
Yep, just-
zapping stuff with
Yeah.
a laser.
Yeah,
Robots
for
with
science.
lasers. What can possibly go wrong?
Perfectly safe.
Excellent.
That's cool. And that's very cool for you, the roboticist who
Exactly,
works
yeah.
on
Yeah.
teaching robots.
Yeah,
to
they're
do
getting progressively smarter and
Yeah.
progressively more capable of acting with a little bit less oversight from us back
Yeah.
here at Earth.
Awesome.
Cool.
There's some questions.
What do we find out from these rovers from Curiosity or
We've
some of these
learned
rovers?
many things, but maybe the one that is interesting to the question of life on Mars is it provided the first clear evidence that there were environments on Mars 3.5 billion years ago that could have sustained life as we know it. Microorganisms on Earth would have been happy
Really?
in those environments. That in
Wow.
that case is a lake environment,
Yeah.
which had plenty of water. It was long-lived, and the chemistry of that lake was completely compatible with life
Wow.
as we know it.
It was so similar.
It was very similar,
Wow.
and so the conditions were there for life to exist and to thrive. And that's a major discovery.
So that's big news.
Yeah.
So water is kind of the key to all this. It
Water
seems,
is the
right?
key, and
Okay.
the progression of those missions is being precisely follow the water.
Follow the
the water
water.
because we
Okay.
need it's important for life, and through following the water, we've reached these environments on the surface that it's clear that they could have sustained life in the past.
Yeah. How did we first find water? That was one of the robotic missions, wasn't it?
Yeah, actual water would be the Phoenix mission, right?
That's right, yeah.
Which was another stationary lander like the Viking that had an arm that could scoop up soil and collect samples.
Yeah.
Okay. We have a photo of that as well. An image of the Phoenix lander that you
Oh,
can
nice.
describe.
Yeah.
Oh, yeah. Is
Yeah.
that the arm that's scooping?
Yep.
Yep.
Yep. So that can reach out and collect soil samples.
Yeah, like Viking was a lander, it didn't move.
Mm-hmm.
In reality, we had an idea that there might have been there's water on Mars based on orbital data, but Phoenix truly confirmed those observations from orbit, and it confirmed it by digging a trench in the soil and exposing water ice,
Oh, yeah.
and then analyzing some of that ice.
And it was at the poles, right? Yeah.
It was near the North Pole, and based on what we know from orbit, it's as you get closer to the poles of Mars, either in the North or the South Pole, ground ice becomes more and more abundant and close to the surface. And in fact, the Phoenix side, it was just a few inches under a cover of dry soil.
Okay. Very cool. Okay, so water ice, it has found Phoenix.
Yeah.
And you told me it made another big discovery. Tell me about that.
When Phoenix analyzed the ice, it actually tasted the ice. The first time we taste ice from another planet.
How did it taste?
It tasted salty.
Salty.
And that was interesting. Not very salty, but it did have some salt.
I see.
And the salt turned out to be another very interesting discovery from Phoenix. One of the major salt components in the soil is called perchlorate. It's a molecule that nobody really cared much about, except in the rocket fuel industry, because it's actually rocket fuel.
Really?
But once it was discovered on Mars at significant abundances, everybody became very interested.
Yeah.
Why is it there?
This rocket fuel substance, all perchlorate.
Exactly.
it's
Why
called,
is it
right?
Mars covered in rocket fuel?
All right.
And so it turns out it's a natural compound. It's found on Earth as well, in deserts and whatnot. And it's a compound that some microbes on Earth can actually eat and use as
really?
an energy source. Yeah. So that became a very interesting astrobiology result. An energy source for life sitting there on the surface, very close to water ice.
Wow.
But the other interesting thing about perchlorate is that it's a very reactive compound. It's not reactive at room temperature. You can have perchlorate here on the table, and it's not going to happen, and nothing's going to happen to it over millions of years.
Oh, really?
But if you expose it to radiation, as on Mars, the high radiation that we get, UV, it decomposes. into very reactive molecules.
Like the sun breaks it down on the surface?
The UV radiation breaks it down and makes reactive compounds just like bleach, for example, the stuff we use at home.
Okay.
And you know what happens when you mix bleach with chicken soup?
No.
What happens is that you get gas released. And you get very similar gases as they were released in the Viking experiments 40 years ago.
Mystery solved.
And it happens at a similar rate and a similar abundances as Viking observed. So 40 years after Viking, indirectly, without not actually looking for it, Phoenix found the culprit for the Viking, or the most likely culprit for the Viking biological experiment results.
Finally, an answer.
Yep.
That's crazy. For the people who worked on it, I hope they were still...
Case closed. Yeah, it was very exciting, I'm sure, for people who were waiting 40 years to understand what happened with the mission. Yeah.
Exciting. Okay, fascinating. We've had a bunch of questions coming in. Shall we turn to a question session? We're going to ask you a whole bunch, as many as we can in 5 minutes, and we'll look for rapid responses so we can hit a lot of these. So many to choose from.
Masta asks, is it possible that we might find fossilized microbial life?
That's one of the issues with microbial life, is that they don't leave behind good fossils. Not certainly dinosaur bones that we can excavate and see. And so that's a big challenge. How to find evidence of life coming out of microbes, that they're soft-bodied, tiny and unicellular organisms that when they die, they decompose and don't leave behind. We have some ideas. In fact, when you look at the fossil record on Earth, the oldest evidence of life on Earth, which is dated at 3.5, 3.8 billion years ago, it's actually structures made by microbes, rock structures made by microbes. The microbes are long gone. They just they left the house behind, and what we see now is the house, so to speak.
Okay.
And so microbes can leave behind fossils, but they're hard to find.
How neat. That is cool. I had a question about what methods can you use besides metabolic investigations in these robotic missions? And I think that might be an example.
There are a number. You could think of, if you go to a place where you think microbes might actually be alive and happy, you could bring a microscope. Bring a sample, put it in water, look at the microscope, and if not something swims, it's like a microbe waving at you. Another one could be using instruments that actually analyze chemistry in a lot of detail, organic chemistry, which is what we think life is going to be made of, organic compounds. And we can search for patterns in that chemistry that are too complex for something non-biological to produce. Biology makes very complex organic compounds, things like DNA and proteins. And so if we find something like these, would be like finding a skyscraper on the moon. It's like, somebody must have built it.
Somebody built that. Yeah, I see. Okay, well, that was a question from Jets 115. That was a good one.
Andy H87 has one for you, I think, Michael. What would a rover mission to the poles be viable or particularly interesting?
I think it would definitely be interesting. And I think actually operating in an icy environment, unlike where the rovers have been driving, would be a lot more interesting, a big challenge, and also interesting. But then there's also the worry about planetary protection, right? Because if we don't want to bring things there, and if there's ice there, we could conceivably make water. And if we make water and we have microbes on the rover, then there's the risk that we could bring our own microbes there and pollute the planet.
Something else to worry about on top of everything else.
Here's a related question from Trablador. How long would it take to be certain there is no life, and so we wouldn't have to sterilize everything we send? Could you ever be certain? You
can never be certain. I don't know you could ever be certain, because we're used to the Earth as a planet where it's covered in biology, but sometimes when you go to some places on the Earth that are extreme, life is not everywhere. It's hiding in very specific places.
I see. Yeah.
And if you can imagine a planet that is extreme like Mars, maybe life is sitting somewhere in a very tiny place, maybe kilometers deep.
Oh, right. Oh, wow. Okay.
So how can you be sure of that it's not there? So we always need to proceed with caution, I think.
Yeah.
Smilebringer asks, what about non-carbon-based life forms? We usually base life upon life on Earth.
There are good reasons why we are made the way we are, and there are some of them are reasons that are hard to. There's only so much you can bend the laws of physics and chemistry to make things work, and there are ideas about non-carbon-based life, but there are so far no places in the universe that we know of where non-carbon-based life could exist. There might be there, we haven't found them, and so. to start searching, it's probably a good idea to search for first things that you're familiar with, that you can recognize and you know where to search for, rather than search for things that are so different that we, again, might not be able to recognize it even if it's standing in front of us.
I wonder if that's related to this question. So let me throw this out from DeathShaft20119. Why follow water? We don't know for sure that organisms live only through water, right?
Yeah, it's a good point, but it goes back to what we were talking about. Mars had water. Other places in the solar system had water. We know what life in water looks like or is made of, thanks to Earth biology. So why not go there? It's a familiar place.
Right.
If we find it there, one of the interesting reasons why we search for life is because once we find life 2.0, even if it's water-based and carbon-based, but very different from us, then our ideas of life will change, will expand, and then maybe we can think more seriously about life that is completely different from us.
Yeah.
But I think we need life 2.0 before we can make that big step.
That's so exciting. I remember maybe a year ago, the three of us had a conversation, and you were telling us that even if you found one dead microbe on Mars,
we don't discriminate.
You would be completely satisfied.
That's
and
right.
Super excited about that.
That's right. Dead microbes, living microbes, and in fact, if we find a living microbe, we have to kill it in order to understand it. Unfortunately, but yeah, even a dead microbe, even a fossilized dead microbe, half decomposed, would revolutionize our idea of life, biology, and everything. So
exciting.
Very exciting.
So exciting. Yeah.
All it takes is one.
Just takes one. That's right. Yeah.
Zoladair asks, how do you program a robot to search for life? What sort of decisions do you have to make in order to search the most likely locations?
Well, the first thing is you have to identify what the most likely locations are. And the way you do that is actually talking to people like Alfonso, and they'll say, go here, this is cool, we should look at that. Then when it comes to programming the robot, there's a lot involved, from just basic things like getting the robot to physically move in the environment, and then making smarter decisions. And that's really, again, about taking sensor data and then trying to say, yes, this is something valuable. And traditionally, we've, again, consulted with scientists and try to say, well, things that look like this is good. Things like that look different, we ignore. It's a very involved process.
Takes a village.
Yeah, it does.
Or two.
Yeah.
Thanks.
A village or two. Nice.
It's always exciting to see the scientists and engineers really working their magic together.
Yeah. That's exciting. I like these projects.
Yeah.
Well, here's an easy one from JB the Dev. How do you boil down, is it life, to a quantitative value?
Oh, yeah, easy.
Easy.
Okay. I'll let Michael take this one.
Yeah. So basically, right now, we can't say, if this, then life. And perhaps the best way to do it is to try and extract the judgment of the scientists by studying how they behave. And so machine learning techniques are kind of a promising approach for that. So eventually, I'll just sit and watch Alfonso long enough, and I'll write down everything he does, and I'll run it through a small Python script, and then I'll ship that out into space.
That's right. That easy, and then my job is done.
Yeah. But it's not that simple. I mean, it's a very involved process.
It is. And if you think of the end members are easy. Something waving at you, yes, and something like a meteorite that there's nothing in there, easy. The problems are all the gray in betweens. That's the difficult part. That's
But that's also what drives you guys, I'm
yeah,
sure.
Exactly. That's the passion. Yeah.
And I guess something else to say is that it's not one thing. It's an accumulation of evidence from different observations that we eventually collect to build confidence that we've seen something that might be life.
Yeah, good point. It's not
Not just looking for one silver bullet. It's got to be.
In science, rarely you get a silver bullet. You get a lot of smoking guns, a lot of smoke and no guns, some guns without smoke, but no silver bullets.
You're too demanding, Alfonso.
Yeah.
I think we have time for a couple more before we move on. Do you have one lined up? Or I got one. G Nintendo asks, what amino acids, if any, have been detected on Mars?
None so far.
None so far.
Isn't that good? Isn't that good? A good place to start. We've found amino acids in other planetary bodies, small bodies, asteroids and comets, but.
Sorry, those are interesting because they are building blocks for proteins, right?
They're interesting for two reasons. One is because life on Earth universally uses them to build proteins, which are very important molecules. The other one is because they are nature provides them for free. Amino acids are present in meteorites. They can form abiotically without the presence of life. And so you would expect them to be available for life to emerge pretty much in any environment, as long as the environment, they can survive that environment.
Okay.
And so they are what we call prebiotically, before life, available.
Oh, nice.
And so it's a good place to start searching for evidence of
So
life.
they're a common ingredient.
They're
So
common
if
ingredients.
everything else lines up for life to emerge, you've
Yeah.
got your amino acids.
Exactly, yeah.
Okay, all right.
But we haven't found any on Mars yet.
All right. Keep
There's
looking.
another one
Yeah.
from MDM PhD, Dr. Furlong. What excites you about the future of robotics on other worlds? What robot would you send to space?
I'm prepared to send any and all robots to space.
An army. Robot army.
Well, exactly, right? And so one of the things that humans like doing when they're exploring is breathing oxygen and eating and coming back. Whereas robots are less demanding on that front. And so if we're going to really explore farther away things and things that are environments that are much more hazardous, robots are in my
Our best
biased
friends.
opinion, the thing to do, yeah. So I think planets, the moon is still, there's a lot to learn there. Mars is great. Europa is another possibly exciting location.
Moon of Jupiter, right?
Yes, yeah. And that actually has the potential to have, it's an icy world and might have water on it as well. So.
Grad students are a good alternative to robots. They're not very demanding, so grad students.
Send one of those to Europa.
Yeah, been there, so
Yes, you know what it's like.
We need the grad students to make the robots work.
that's true. That's true.
So, yeah, that's a call to everyone who wants to get
Yeah.
involved. These guys need grad students. So there's a comment that will lead us on to the next topic I want to talk about. I want to hear about some of the new tools that you guys are developing and kind of where you want to look and how that determines how you're going to look. So this comment was from Hobbs555. I guess if there is life on Mars, it's deep underground? Is that how you
Good
guys
guess.
see it too?
It's a good guess.
Yeah. Does that drive what you're working on?
Yep, indeed.
future?
If anything we've learned about Mars is that the surface is extreme, but maybe as you get deeper and deeper, conditions become better and better. And so then there are good reasons for it. As you get closer to the center of the planet, temperatures go up, and we know there's plenty of ice buried under the ground. So at some point, theoretically, that ice should melt,
Ah, yes.
create maybe a habitable environment.
Yeah.
As you go deeper, also, some of the nasty things you get on the surface, you don't get at depth, like radiation. And so it's, as you go deeper, you're more protected from these things. So
Yeah.
it's a good bet if you go deeper.
Okay.
It's also harder.
Yes. Getting
So is that something you're working on, like how to go deeper?
We are.
Yes, yeah.
We ask, and then now the ball is
Okay.
on their court to come up with ways to do it.
I see. So you roll up at Michael's office.
Yes, I said, Michael, get me
I wanna
2
dig.
kilometers, and
Get
then,
me 2 kilometers
then I'll
down.
come back 10 years later.
I'm going to need a lot more grads.
Right.
Yeah, so we're actually, we're developing a smart drill right now.
Smart drill.
Yes, yeah.
Okay.
And so we want a smart drill because, again,
What does that mean?
well, it's a drill that deals with the problems it encounters so we don't have to.
Okay.
And so all these robots, they're far away. It takes, on Mars, it takes about 20 minutes to get signal back, right? So you can have encountered a problem before the drill can have encountered a problem before we even know that it's going on. And it could be too late at that juncture if it just keeps trying to just drill as if everything was normal. So the smart drill tries to recognize problems and then fix them by basically by trying to feel how it's behaving. So if you're drilling at home, you're putting a screw into a piece of wood. If something goes wrong, you can feel the drill shakes, or it hits a knot and it just starts skipping, or you thread the screw, or you strip the head of the screw. You feel that it's not right. We can do similar things with our drill. We can look at vibrations. We can look at how much power it's drawing to do the drilling. We can look at the temperature, how hot it's getting, and we can use that to then try and decide, okay, this is a particular kind of fault, and there's several different kinds of things that can go wrong with drilling, and then we take particular actions to fix those problems. And so it can be things like there's a rock between the drill and the hole that it's drilling, and it just sort of binds up. Or there can be soil falling in, and it can't clear the hole fast enough, so it's not making progress. So yes, we instrument the drill, put lots of sensors on it, look at what data is coming back, and say, okay, this is a binding fault. This is we've hit a hard surface we can't penetrate. Here, take the appropriate action.
Yeah.
So the drill itself can actually figure that out on its own now? Is that what your goal is?
That's the idea. Yeah, and we've
Okay.
been teaching it to be a smarter drill.
The problem is that Skype calls between Mars and Earth are really, really bad. It takes about 20 minutes to get a hello back.
Wow.
And so we cannot rely on instruments there.
Exactly, and especially if we're drilling into like icy surfaces, right? We could conceivably melt the walls, and again, creating water, which is a planetary protection problem. But it could also possibly refreeze and get the drill stuck in the ice indefinitely, and that would be the end of the mission.
And we can, that drill cannot wait for us to learn about it, decide what to do next, send the information. By then, it might be too late.
Right.
I can imagine trying to have a conversation with you, and 20 minutes later, I get a
Right.
response back.
Imagine that.
Hello, Abby.
Right. And if you're asking for instructions, or Abby, I messed up.
And
My
you
drill
might-
is stuck. What do I do?
And you might only
It's
get
too
2
late.
chances in the day to say something, which is actually
Yeah,
the
that's
case
crazy.
on Mars. So
Well, that really underscores the need for some kind of autonomy here, like
Right.
right?
Smart-
It's got to
smart
act on its
robots.
own a little bit. Yeah.
Diagnose its own symptoms, right? And
Precisely.
So you've said it can back itself out, or it can hammer through a hard
Yeah,
thing,
so
right?
the drill we're developing is a rotary percussive drill, and so that means it can drill in like a normal drill, or it can start hammering to break up whatever it's drilling through to make it easier to make further progress with the more standard drilling approach.
Cool, man.
Wow.
Sounds good. I'll take
So
one.
we have sent drills to Mars before, though, right? Can you tell us a little bit about?
Yeah, so Curiosity actually has a drill. It's similar. It's a rotary percussive mechanism, and I have here this. This is just a drill that I took from our machine shop. So this is not to scale. It's not an accurate representation of what MSL has. Curiosity.
Yeah.
So Curiosity's drill is a little bit fatter, and it's gets about a 5 centimeter depth. So something about this length.
We actually have video of it drilling
Yes.
that we could watch right now. On Mars, Curiosity is going to put down its
Cool.
drill.
That's the arm with the drill, yeah.
Yeah.
And this whole drilling process takes about 25 minutes.
Okay.
Right. And again, it takes 20 minutes
Wow.
for the start of the drilling to get back to Earth. Right?
Oh, okay, yeah.
So it's almost done by the time we'd find out it's begun.
Okay.
So if something goes wrong,
At the start, you're way too late. Yeah.
exactly.
So it's on sped up right now.
Yes.
Yeah,
right?
that
And
video
it's
is-
also on a loop, right? So
Yeah.
we're seeing
Yeah,
it.
yeah.
Right. That's a slow process, though. I see.
Yeah.
It's not like my.
Meticulous.
It's meticulous. Yes.
That's the
Pardon
right
me,
word.
Curiosity. Okay, so it's drilling into Martian rocks. We have photos also of holes that it's drilled, which is kind of fun because it's on another planet and it looks just like a drill hole at home. Can we see the image of a hole drilled by Curiosity? Yeah, look at
there you
that.
go.
Yeah. So the big hole is the drill hole. And then that gray material is the stuff that was cleared out of the hole as was making progress. And then there's that row of little holes. That's where the laser zapped it to sort of vaporize what's there
yeah.
and see what the rock is made of.
So I have a question. Why is it gray? Why is that powder gray?
We run out of paint.
Yeah. so Mars is known as the red planet, but it's covered in rust, oxidized materials. That's why it's red.
Okay.
But it's not red all the way through.
What?
And that gives you a good idea of why it's important to go deep, is because it's the depth dimension is another world.
Yeah.
We would have never
yeah.
learned that if we hadn't
Yeah,
gone.
yeah.
Imagine what we can do if we go even deeper.
Right.
We might learn things
Right,
that
right.
were completely unexpected. That was unexpected.
So Curiosity taught us that it's not really a red planet.
Not inside.
Not in its heart.
Not in its
Not
heart.
a planet.
Not inside.
I had
That's
no
right.
idea before I saw that photo.
It's pretty
I
cool.
seriously didn't know.
And it might be red in other places.
Yeah.
So if anything we've learned about Mars is that it's very different. It's
yeah.
not the uniform planet once we thought it was.
Which is why the rover robots are so important, right?
Yep.
We can't just characterize one little
spot.
region.
Oh yeah,
That's right.
right.
We need to move
Yeah.
around.
Maybe you land in the one spot that is gray
Right.
underneath.
Yeah, I mean,
or
imagine if
whatever
we
it
were
can tell
like, 10 feet over from where life was.
Yes, yes.
We missed it. Yeah.
So we've looked at the Curiosity drill. You've shown us how big that is. What are you working on now?
Oh, yes. This is the drill that we're working on. It's slightly bigger.
It's a little bigger.
A little bit bigger, yeah. So what you see here is these ridges here, it's the flutes, and this is what lifts the material out of the hole.
Okay.
Right? And so we drill this, it's about 3 feet long, and then what we really care about is this last 10 centimeter bite here at the bottom, and you'll notice that the flutes are much more tightly spaced.
That's flutes.
Yes, yeah, the ridges, the ramp, right? Because this is it's a ramp. It pushes things up and goes out the top of the hole.
Right.
So again, they're denser here because we don't want the material to move by too quickly once we've hit the depth we care about. and then we pull this out of the hole up to a sample collection device, which then takes the soil to the instruments.
Gotcha.
For analysis. Yep.
And, yeah. And then we look to see.
And then we look for things like microbes or
Yeah.
organic compounds and things like this.
So what is this hole here? I'm looking down a hole right there.
Yeah, so there's a hole in the bottom, and that's for cables to go down. Because again, this is a smart drill, and smart means sensors. And so
Okay.
we have in this drill, we'll have a temperature sensor to see how hot it's getting, because that tells you like how hard is it to drill into to what you're drilling to. And then it also has a conductivity sensor, and
What does conductivity mean?
that'll help us detect if we hit water or ice
Yeah, or
in the hole.
or we're making liquid water.
Yeah.
If there's liquid water, it's going to send a signal. If it's dry, no signal. So
And why is that data useful? What does that tell you?
well, it tells them, or it tells the drill how to operate, when to stop, when to proceed. If it gets very hot, you might want to stop and let it cool down. One reason might be planetary protection. We don't want to create an environment, if we're drilling in things like ice, for example, we don't want to create an environment where microbes, especially microbes we bring with us, might grow. Planetary protection. But we also can learn about what's the consistency and the strength of the materials we're drilling into. So it's information that is good for the science, but it's information that is good for the health of the drill.
All right. So this you would attach onto a rover or a lander.
Yeah.
Right.
Yeah.
Okay.
Whatever vehicle's taking the drill to the places we want to drill in.
And that's something you test
Yes.
on Earth, right?
We do. Yeah.
Right. So right now, I believe.
in fact,
In fact, right now.
as we speak.
Right now.
Right now?
Yep.
Yeah, we've got a team of scientists down in the Atacama Desert in Chile, and they're testing a version of this drill in an actual simulated environment.
This minute they should be drilling a hole.
This very
Yep.
minute.
Yep.
If they're not,
If they're not,
Alfonso
yes.
is going to be upset.
We got some
have
video.
footage,
Yeah, some great footage we
from-
brought. We
from
got sent back to us here
Yeah,
at
yeah.
Ames from the Atacama.
Yes.
Yeah, so this is the drill site, and
That's
so
from a few days ago, I think.
yeah, and that's where the scientists are set up and that's our workhorse robot K-Rex 2 mounted with
K-Rex.
the
K-Rex.
K-Rex 2.
K-Rex.
It's our
Two.
Ames
Okay.
rover. Yeah.
And there you can see the drill, and the blue structure is the arm that we use to collect sample and deliver to the instruments.
Nice.
And it's digging.
Yeah, you see
in.
the drill turning. Yeah,
And
yeah.
that gear right there is where the sample comes out of the drill when it pulls back up, and the bucket is the cup. And here is one of our researchers just observing and taking notes on the experiment as it's running.
Look at that landscape.
Mars.
That looks a lot like the Viking picture we saw a little while ago from the surface of Mars. It's
truly
really
is
Martian.
Mars on Earth. Yeah.
Yeah. So cool.
What is it? Yeah, tell us a little bit more what it's like to be there, because you guys have been there yourselves, right?
Yeah. So that's the reason the drill is there and the rover and the scientist. This is part of a project called ARIDS. It's the Atacama Rover Astrobiology Drilling Studies.
Yes.
Mouthful.
It's quite a mouthful. And the goal of the rover of the project is to precisely learn Mars science on Earth. So go to the driest place on the planet. That's the Atacama Desert in northern Chile. It's the driest place on Earth. It's what we call in astrobiology, in planetary sciences, an analog environment.
Analog, okay.
Analog that
Yeah.
is similar, not exactly the same, but very similar to places out there on other planets. And so it allows us to do science and test engineering without going to those places before we go to those places.
Right. Getting
Make sure
ready
that
to
it
go to
work-
those places,
Yeah, when
right.
it comes to engineering, make sure that things work properly in environments that are similar to the places we want to go. When it comes to science, it allows us to understand things like what happens if you add chicken soup to soil that is very dry. Then when we go to Mars and do the experiment, we can kind of predict what might happen.
Right.
And so that's what ARIDS is doing. It's preparing NASA to search for life on other planets by going to the Atacama Desert and testing this instrumentation.
That's so cool. I love these projects.
But as dry as the Atacama is, we still find life there.
We do. This is the Earth. It's hard not to find life. And so it's a place where we can test how good or bad our instruments are. It's definitely a place where if you don't find anything, maybe you don't have the right instrument.
Okay.
Because we would expect life on Mars, if it was present, or fossilized life on Mars, to be a lot less abundant than even the Atacama Desert.
Yeah.
It's a lot worse of an environment.
Yeah. Because you said Mars is 1,000 times
Yes,
drier
yes,
even
so
than the Atacama, the driest place on Earth,
Take
right?
the Atacama, the driest place on Earth, where you've been there.
I have. Yeah.
sunscreen, sunglasses, a
I
hat, and plenty of
confirm.
water.
It is
Yes, it's
dry.
really, really dry. It's so dry that no plants or animals survive.
There's
The only forms of
nothing.
life that survive in the driest parts of the Atacama are microorganisms, and they're not doing very well for that matter. And
really?
so, but then take Mars, and everything we know about it, it tells us it's 100 to 1,000 times drier than the Atacama.
So the idea is if you can't find it in the Atacama,
You
you,
can find
don't
it in-
stand a chance on Mars.
On Mars, yeah.
Okay.
If you find it in the Atacama, you might still not be able to find it on Mars because it's so much more extreme. But the Atacama gives you that confidence that if you find it there, maybe you're on the good track, on the right track to find it on
Yeah.
Mars.
So this is kind of like a test case for Mars in a
It's a
certain
test
sense.
case, yeah.
I like to call it a dry run in the driest desert on Earth.
No pun intended.
Very much intended, but it's okay. Yes.
Yeah.
But fascinating. So, yes, I did get to go last year to cover the story.
Yep.
And there were lots of scientists there last year working in the field. But this year, what's different is a whole bunch of you are here.
Yes,
this
that's
year,
right. So this is the fourth year of the project. It's the fourth time, I think, the team goes to the Atacama. In the previous years, it's been a lot of science on the ground. And testing different pieces by themselves or integrated into the rover.
You're taking soil samples. and
Analyzing it. So we're doing
Yeah.
a lot of things. But this year is special because what we're doing this year is simulate a Mars mission. And so we have boots on the ground with the rover and the drill and the instruments. And then we have a backroom science team here at Ames directing the rover what to do, receiving data from the rover, and based on that data, giving the next steps, instructions on what to do next, just the way you would do it on a Mars mission.
Yeah.
And that
So
way
you would have a team of scientists back on Earth.
Every morning,
trying
9
to-
a.m. this
yeah.
week, we meet, we get the data that the rover collected the previous day and the instruments. We analyze that data. It's not processed data, it's quick looks that we call, which
Okay.
tell us, yeah, you got the sample, you got the data, it looks good, move on. And based on what we learned, the few snippets we get from those data sets, we decide, well, go there and get that sample or go deeper and get another sample. It's a tactical decision that we need to make on the fly, pretty
I
much.
see. You call it dirt to data, right?
Dirt to data,
All
yes.
that's happening on the rover.
Thanks to intelligent rovers that we can tell them, pick that up, and the next thing we know is the composition.
Thanks, Michael.
No problem.
Cool. Right, but no, I love that term because it makes it really clear that the rover is drilling. It's pulling up dirt. It's taking the sample, throwing it into the instruments it carries.
It's doing all those
Yeah.
things. And then the instruments are processing the sample, analyzing the sample, and sending the data. And humans are not in the loop.
Yeah.
Wow.
That's so exciting.
Airplane Man 1997 says, "That's cool."
He likes
I think
to
we can
drill.
all agree on that. Yeah.
Absolutely. Yeah. Here's a question also about the drill. MGM PhD asks, what material is it made of?
This is steel?
Still,
Yeah.
yep. And it's probably something like this that we would send.
Yeah.
Yes. All right. Quick.
Trap Ping Bin asks, how much analysis can be done directly on Mars compared to how much can be done by bringing samples back to Earth?
So that's a good question. There are two different levels of analysis. You might want to do a preliminary, very quick analysis to check the health of the instruments, or to make sure that you got data. Yes, no, and that has very little science involved. But then that data gets transferred, sent to us, and then we have all the time in the world to look at it carefully and analyze the details. Obviously, we might want to make decisions quickly for the next steps for the mission, but all the data gets saved in a repository that scientists pretty much around the world can access and analyze and look and tease out over many years. So we're still looking at Viking data.
Oh, wow.
And so, that science can move. It moves a very hectic pace at the beginning in the mission, but then we have all the time in the world to actually dig through the data and understand what's going on.
We do have a mission where that's looking at caching samples, right, for bringing
That's
back.
That's
right?
right. Yeah, the next one, Mars 2020.
Yeah. And that's sort of the follow-on from Curiosity, and it's going to a lake bed, right?
It's
And-
going to another lake, or what we think was a lake based on what we know from orbit. Yeah, and it's going to be the first step in a campaign for sample return to bring samples actually back to Earth.
Wow,
Very exciting.
Yeah.
Dr. Riot asks, any plans in the future to take samples from the areas where we see seasonal brine flow on cliff faces? So that's someone who's been following the Mars news.
Yeah.
So that salty water was found flowing. Right?
There are intriguing observations on the surface of Mars. We're still trying to figure out what the cause for these patterns is. But there is one possibility: there is liquid water or salty water, and so that would be like a, for astrobiologists, that would be a beacon. Come here and take me, sample me. But it's not easy. There are many places we would like to go, and normally the places we want to go are the most challenging ones. They're always on the slope. They're always in a difficult environment. So for whatever reason, it's never easy.
Yeah.
But this is definitely one of many places we would like to go and collect samples. Yeah.
So, okay, the challenges of drilling off-world makes me think of plans for the Artemis program. So NASA is heading to the moon
We are, yeah.
in 2024, and I think that's going to be part of it, isn't it?
It is, yeah. And Artemis is the trip back to the moon where we're sending the first woman and then more men to the moon, presumably, at some point. And so if that's setting up to be long-term habitation on the moon, and one of the things we need to do is try and get resources there, right? So we've recently found out that there is water on the moon, which is kind of surprising.
There is frozen ice crystals, right?
Yeah.
Yeah.
That's hard to extract. It's an icy material, right? And again, you will want a smart drill to try and be mitigating the risks of drilling into these icy surfaces. So stuff like we're doing on ARIDS actually feeds into the Artemis mission, which
I can see
is
how,
really kind of cool.
That is exciting. Great.
So it's a multi-purpose drill potentially for many
Sounds like it.
locations off-world.
Yes, yeah.
Yeah, I like that. You've got the scientists working with the engineers for the Mars search for life, and it's also going to be really helpful when we get to the moon.
Yeah, it's an example of how exploration drives exploration. It's and a wheel that doesn't stop turning.
Yeah.
It's pretty cool.
So cool. I love these things.
Here's a question I like from Airplane Man 1997. What would the drill sound like on Mars?
That's cool.
That's a great question. The atmosphere is a lot thinner.
Yeah.
So it would certainly be quieter.
What does it sound like in the Atacama? Does it have a sound?
It would sound. What does it sound like in the Atacama?
Like a jackhammer.
Yeah, when it's hammering.
Slightly higher pitched
Does it
jackhammer.
really?
Yeah.
That's what it sounds
Okay.
like when you're sleeping, trying to sleep in the tent in the Atacama, and the engineers are testing the drill. That's what you.
Also, if it's drilling into something hard, there's a high pitched squeaking noise. It
Yep.
could have like,
I remember the
Yeah,
squeaking
it's
noise.
Definitely not white noise.
No.
But no idea how it would sound on Mars?
Quieter, maybe
Muffled,
higher pitch?
Yeah,
maybe?
or lower. I don't know.
Or-
Actually, it's a good question. I don't know, but it wouldn't be quite as annoying. Actually.
And there wouldn't be anybody there to have to listen to it.
Yeah,
At
yeah,
least anytime
Nobody's
Not
sleeping
yet,
in the
yeah.
tent.
Not yet.
Yeah, not yet.
Yeah.
Also,
Unless there is life on Mars.
Unless we
That's
can ask
true.
them once we find them.
we arrive and we're the worst neighbors
But you think of
ever
the
as soon
drill
as
we
we get
sent
there.
and the noise we made.
Right?
Yeah, exactly.
Also about the Martian environment, Lejours Pro asks, is Martian gravity similar to what we have on our planet?
No.
Right.
It's about a third, I believe.
Yeah.
And so
Does that affect the drill and how you have to design it?
That's a good question. So when we're drilling, we apply force.
Yeah. And gravity helps.
Yeah, it does. And actually, that would, I guess, affect the rate that we could extract material from the hole.
Yeah. So to compensate for some of the weight loss that you get on Mars, if you wanted to
Yay.
diet, to compensate for some of that, we actually have to add some weight on the drill so that it can push
Okay.
downwards
With enough force.
with enough force to
Yeah.
go through layers. Yeah.
I see.
So it has an effect.
Yeah.
All right. More questions.
Regal 16 asks, does the drill go straight down, or does it have the ability to change directions or even go horizontally?
Straight down.
It's a straight one way.
Yes, yeah, at least
Okay.
in the setup that we're doing in ARIDS. You could conceivably try and do slant drilling, but that would be a more complicated problem again.
And risky.
Yeah, because it could go off to one side or something if it
Or even snap
Yeah.
if you force it too much. Yeah.
Uh-huh. Yeah.
It's made to go straight down.
Straight down. Okay. Space TV Internet wants to know if both of our guests, you guys, could be on the surface of Mars tomorrow. What would be the first thing you would do to search for life? Start digging. Bring some chicken soup.
That's a good question. Well, I have, as we mentioned earlier, the surface of Mars is very different. Wherever depending on where
it's
you go, it's a very different
Buried
environment.
all over the surface.
And
Yeah.
so if I was at some places like near the polar caps, I would get some of that water ice, melt it, cup of tea maybe, and then put it under the microscope and see if something swims around.
Okay.
If I was in a place like where Curiosity is, ancient rocks that formed in a lake bed 3 billion years ago, I might get some samples and run them through very sensitive instruments that can analyze the chemistry and search for those traces of dead microbes, maybe. If I could bring Michael with me and he could drill 2 kilometers, I would just wait on the surface until we get the sample and then see what's there, if something is actually lurking down there. So it depends on where you are.
Yeah. It's a, well, it certainly was a varied environment. It still is a varied environment from a geological perspective. So it's just like not one place isn't enough if we want to increase our odds of finding life. We go all over.
Yeah.
Kubameister09 asks, how long would it take from discovering to confirming to publishing that life has been found?
Yeah.
Scientific process.
The scientific process.
Kind of like, what would it take for you to be sure?
Well, I guess it depends on what you find. If you find something waving back at you, don't even publish. Just put it up on the web and let everybody enjoy it.
Would they believe you?
Would they believe you? That's a different story. If we find, it's not going to be probably such clear cut. It's not going to be a straight path. It'd be surprising. Science rarely works that way, that you have a clear path from discovery to publication to acceptance. And especially with things so important and groundbreaking as finding life on another planet. So it's going to take a while to process the data. I wish it was clear cut, but if not, then there will be debates. There will be meetings and conferences where people will go and have a back and forth. Eventually papers will be published, and then the scientific method demands that we don't stop there. We try again, we continue, and we confirm or disprove those results. And it's that process of building on results and testing and new hypotheses and new experiments, what in the end either provides the evidence that we need or not. So,
and so, like with Viking, it took about 40 years.
Yes.
So,
For example.
And not everybody's, and there might be people out there that were not convinced of the perchlorate explanation. And it's a valid thing in science that you can always doubt, you should always doubt the standing explanation. So
And keep testing
and keep testing.
and all that,
you can't prove things right, you can only prove them wrong.
Right, exactly. Yep.
All right, good one. Quick question from Digital Donger. Will Mars 2020 rover have any instruments for life detection?
It does, in a sense, because 2020 relies a lot on doing a lot of the science when the samples come back to Earth. The focus is on smart instruments that can identify the right samples to bring back.
Okay.
And so that doesn't require really analyzing every element in that rock to know exactly where it came from. We can do that back on Earth when the samples come back. But we do need instruments that can tell, well, between those two samples, this looks like a better sample to cache and preserve and bring back to Earth because of its composition. It might be different and things like this. So those instruments are selected precisely to do that. Select the best possible samples for return.
Okay, neat. From MDM PhD, what have we learned about Martian dust or dirt that would impact robotic tasks? Is that something you're learning from the ARADS project and the Atacama? How does a rover deal with the dirt?
We're actually having an interesting problem in ARADS right now, in that when we're drilling up dirt, we have a camera that's looking at where the dirt comes out and goes into the scoop, and the dirt is all getting stuck to the lens of the camera, which is a problem for cameras, because they need to be able to see to be useful. So that's that kind of that mitigation, dust mitigation is a big thing.
That's a problem. Wind is a problem. Do you remember we have this scoop that is collecting cuttings from the drill and then brings them to the instrument? If you have strong winds, your cuttings might blow out of the scoop. So we learn how to position the scoop and the rover in a way that it blocks the wind and prevents sample loss.
Okay.
Okay.
So we learn a lot of things.
Nice.
All right, keep going, ARADS. We need to know these things before our rovers go to Mars and start drilling. But that is all the time we have for today. It goes so
All right.
quickly. But thank you so much to you guys for joining us today.
Thank
This
you.
has been fascinating. And thank you to everyone who joined us in the chat on Twitch. Join us next time. That'll be October 24th for our second annual NASA-themed Halloween costume and cosplay contest. So it was a lot of fun last year. Join us for that. Thanks for watching, and we will see you next time.